Welcome to the fourth live sessions on mechanics and control of robotic manipulators. I am Isaac John. I'm the TA for this course offered by Dr. Shantakumar from IIT Palakkad. So we have so far covered week 3 worth of contents in the previous week. So today we'll be mostly focusing on the topics that we have covered in week 4, which are the introduction to differential kinematics. So this week preliminarily dedicates itself to differential kinematics, rather forward as well as differential kinematics, as you can see in point 1. We also established the velocity propagation model for serial manipulators and how to set up a Jacobian matrix for a given manipulator. So the velocity propagation is actually very important. Like if you are dealing with kinematics, it will also the velocity propagation metric will also enable you to construct the Jacobian matrix of a manipulator. This is useful for kinematics as well as statics of robotic manipulators. And in the lectures, we have also seen how to propagate velocities, like propagate in the sense how to propagate velocities from the base frame all the way to the end effector, and how to implement that on MATLAB. We have also come across how to model statics. Like, for example, if a problem is given, like if the end effector is subjected to a specific load, then what are the torques, or what are the joint torques or forces that we would be giving so that the robot would maintain static equilibrium. So problems related to manipulator statics we have also covered in week 4. And we have also given a basic introduction to model the dynamics of the robot using 2 different methods called Lagrange-Euler methods and Newton-Euler method. But if you have gone through the assignments, we are mostly limiting our assignments to up to statics. We are not covering dynamics for the assignment questions regarding this week. It's only we are limiting ourselves up to statics. So in that regard, we'll discuss the topics regarding dynamics in the next week. So yeah, that's about it. So this will be the summary of our today's session. We'll cover up to manipulator statics. Okay, so moving on, I hope the assignments, you have been doing all the assignments for all the weekend, all the weeks until now. I hope it was all right. It was fine. Okay, so we'll begin the session with the kinematic model basically. So as you have seen in the previous weekends, we would establish a kinematic model for the robot as such. So this is nothing but a mapping between the task space variables. So the vector mu is nothing but the task space variables. This is where we would define the task of the end effector, like the coordinates in which we would define the task to be done by the end effector, and the vector q is nothing but the joint space variables. So to extract the differential kinematic model, we are essentially differentiating this expression with respect to time, right? So as you could recall, we have 2 kinematic models, 2 geometric models, in fact, the forward geometric model as well as the backward geometric model. And the same applies for the differential kinematic model as well, where if you differentiate this equation, you would end up with this equation. Mu dot would be a matrix J of Q times Q dot, where this J of Q is commonly known as the Jacobian matrix of a robotic manipulator. The Jacobian matrix. And the constituents of the Jacobian matrix, as you can see, are functions of Q. Q in the sense the joint variables. And the general form of the Jacobian matrix, J of Q, would be the partial derivative of task space variable. This is not u, this should be mu, right? So it should be the partial derivative of mu with respect to partial derivative of q. So this is if you have hard time understanding this concept, you know that the robotic uh, the mapping between mu is basically done through q. So if you want to differentiate mu with respect to time, you first take a partial derivative of mu with respect to partial derivative of q, then multiply this with partial derivative of q with respect to partial derivative of total derivative of q with total derivative of time, where this dq by dt is the term q dot. And the matrices comprising of dou mu by dou q is nothing but the Jacobian matrix. Right? That depends on the structure of the manipulator robot that you are dealing with. So in this regard, this expression deals with the forward differential kinematics of the robot, where if you are given q dot as an input, the joint space velocities as input, you could use this expression to find out mu dot. Right? So the problem of forward differential kinematics is given q dot, find mu dot. This is basically the problem of forward differential kinematics. So this is nothing but an act of simulating or analyzing the manipulator at velocity level. So it's just like the geometrical model. Like if you are giving some sort of inputs to the robot's arm, a robotic arm's joint, how would it translate to the motion of the end effector? So that is nothing but simulating the manipulator, simulation of the manipulator. Whereas in the case of inverse differential kinematics, the problem basically inverts. So if you are given a vector mu dot, then what would be the velocities of all the joints q dot? So you can do that by inverting this expression by multiplying j of q inverse in both sides, j of q inverse, and these basically become an identity matrix, and you would end up with this expression, where q dot is j of q inverse mu dot, where mu dot is the desired velocities of the end effector. So this is nothing but the controlling of the robot at velocity level, because if you want to do a task, or if you want the robot to execute a task, you would define the robot's end effector velocities. And for a desired level of end effector velocities, how would you give inputs to the robot's joint? That is nothing but controlling of the robotic manipulator. But here, in this case, it will be at the velocity level, because you are not taking the dynamics into account, the dynamics due to inertia, acceleration into account. This is purely limited to velocity level. Right. So that is about the two differential kinematics model, the forward differential kinematics model and the inverse differential kinematic model. The forward differential kinematic model is nothing but simulating the robot, simulating or analyzing the robot in velocity level. Whereas the inverse differential kinematic model is nothing but the controlling of the robot at velocity levels. All right. Then in the lectures, we have also covered the Jacobian matrices, where in what case, what would be the common structures of the Jacobian matrices, how whether it is possible to invert Jacobian matrices, right? So if you go to the previous slide, you might have seen, in case of inverse differential kinematics model, you are essentially required to find an inverse of the Jacobian matrix. So if you are given, if you are given an architecture of a robotic manipulator, you would be able to assemble the Jacobian matrix. But if you are given a problem of inverse differential kinematics model, you are required to find the inverse of the robot, the Jacobian matrix. But as you might have recalled, as you can recall, the inverse basically exists if the Jacobian matrix is square, like if it is an m cross m square matrix. And in order for the Jacobian to be invertible, the determinant of the Jacobian Q should not be 0, right? It should not be singular. If it is singular, then the inverse is not defined, it does not exist. But there could be instances where you would come across when the Jacobian is not even square, right? The Jacobian matrix could be a broad matrix like J11, J12, J13, J21, J22, J23. This would be theta 1 dot, theta 2 dot, theta 3 dot. This could be XY. So this is basically a short matrix, but a broader matrix. Actually, it's 3 cross, sorry, it's a 2 cross 3. A broad matrix, you could come across these sort of matrices, right? Yeah, where the task space where the robot would be operating would be of dimension 2, but the joint space, the number of joints of the robot could be more than 2. In this case, 3 cross 2. So like these are the case of redundant manipulators. Like in some applications, you would like to have some sort of redundancies so that it can have advantages. Maybe it can have multiple solutions that could be advantages. It could avoid singularities, or multiple advantages are there. So you could end up with these sort of Jacobian matrices, a broad Jacobian matrices. And there are also cases where you would have a tall Jacobian matrix, something like this. Theta 1 dot, theta 2 dot, X, Y, Z, J11, J12, J21, J22, J31, J32. Here, it's a 3 cross 2 matrix. It's a tall matrix, but a bit narrower, a lean as well as a tall matrix. You could come across these sort of applications. But if that is the case, if these are the cases, then how would you find the inverse of Jacobian matrix? So that is the challenge, right? So as you can recall, if you go purely by linear algebra, there are two cases when the number of rows of the Jacobian matrix is greater than the number of columns of the Jacobian matrix, or in another case, if m is greater than n. So if the number of rows is greater than the number of columns, what does that mean? It says there are more number of equations, more number of equations and unknowns. So what is the implication of these sort of things? More number of equations than more number of unknowns. Oh, okay. I'm getting a message from Perumal Sami. It says in assignment 3, question number 15, option 4 is also correct. Okay. Yeah, I'll look into that. All right. Let me see if I can communicate this to the NPTEL team so we can take the appropriate step. Okay, I've also gotten another query from Saurav. Is asking what is the physical significance of a Jacobian matrix? Yeah, like if you have gone through all the lectures in this week, Jacobian matrix have a lot of significance regarding the regarding the kinematics as well as statics. Just to be in the scope of this week. So as like the primary aspect of Jacobian, as you can see, is simply the mapping between the task space velocities and joint space velocities, right? If you can see, mu dot is nothing but J of Q times Q dot, right? So if you are given a task, so for example, if you are given a task so that you would want your end effector to move with specific velocities in X and Y directions, and you have a RR robot. For example, if you have a 2R robot, something like this. This is the first revolute joint. This is the second revolute joint, and you have an end effector. And your objective is to control the end effector in space with some specific velocities x dot and y dot. And what would be the inputs? What would be the input velocities that you would be giving giving onto the motor, theta1 dot and theta2 dot. So if mu dot is given, you have to find q dot. How would you do that? You could do that by using this Jacobian matrix mapping. Right? That is a major significance of using Jacobian matrix, and that is not the only use of Jacobian matrix. You could also use Jacobian matrices for a lot of other analysis as well. For example, like you might know the concept of singularities of a robot. For example, if this is an RR robot, for example, I'm attaching a coordinate frame, something like this. This is y-axis, this is x-axis, and z-axis is basically out of plane. So you can basically construct a Jacobian matrix depending on the structure of the robot. And what happens, like like typically in case of a robotic manipulator, you would encounter something called a singularity, a singular configuration. For example, like a singular configuration is a configuration where the robot loses a degree of freedom. Right? For example, like in this case of in the case of a 2R robot, I'll show you a singular configuration. In case of a 2R robot, a singular configuration is where the robot's links are collinear. So if, yeah, 1 second, if this is link 1, this is the first joint, this is the second link, this is the second joint. See, the arm of the RR robot is fully stretched apart. So at this configuration, you can see that the robot loses one degree of freedom, right? At this configuration, the robot can only have a velocity perpendicular to the arm. It cannot have any velocity parallel to the arm, right? So like if you fully stretch your arm like this, so consider this to be an arm. If you fully stretch your arm, could you apply a force parallel to the arm? No, you can apply a force, but that force won't cause the arm to move parallel to the in parallel. You could see for yourself, if you stretch your arm and if you try to exert a force parallel to the arm, it won't move. It will be locked in that position. So such cases in robotic manipulators, like singularities can have a lot of detrimental effects. Like you could potentially lose the control of a robotic manipulator. And you can basically study the configurations where the robot becomes singular just by looking at this Jacobian matrix. Right? If the Jacobian matrix loses its full rank, like for example, the 2R robot manipulator has a Jacobian matrix of 2 by 2 of an order 2 by 2. If the rank loses, if it loses its full rank from 2 to less than 2, maybe 1, that means that the robot is at this singular configuration. You would see that in the upcoming slides, in the later slides of week 4. So depending on the Jacobian matrix, you can basically identify whether the robot is near its singularity or near a singular configuration or not. That is the significance of using a Jacobian matrix. It's mostly related to singularities. Okay, so we were discussing about the case where the number of equations is more than the number of unknowns, right? Number of equations more than number of unknowns. So we have an excess number of equations more than the unknown. So in other words, you could also say that the system is over-specified. And depending on whether or not the system is linearly dependent or not, you may not even find an exact solution for these sort of systems. For example, a general linear system like AX equal to B, you can simply find X as A inverse B. But if the system is over-dependent, if the system has more number of equations, this relation might not be even valid because A inverse is not defined for a non-square matrix. And if the number of equations, if the number of axis equations are independent of each other, you may not even get a solution. You may not even get a solution for this problem Ax equals to B. Right? So the only other alternative, the only other way forward is to find an approximate solution. You will not get an exact solution. You can find an approximate solution, and the property of this approximate solution is that the least square distance from the actual solution would be minimal. That is what we are trying to do. So we'll get some A x star, right? And this would be some B star. And the solution for this x star, what we are basically trying to do is we are basically minimizing the least square, the square of the true solution to the approximate solution using some least square approximation. So if you are doing that optimization, you will be able to find out an analytical solution for this approximate solution. So we do that simply by establishing an objective function. So L is basically an objective function that says mu dot minus j of q times q dot. So this was our original problem. Mu minus j of q, mu should be equal to j of q times q dot. But since we are finding an approximate solution, they may not be equal. There should be some small error between mu dot and j of q times q dot. But what we are doing is that we are trying to minimize that error. So simply by minimizing the norm of the difference between mu dot and j of q times q dot. So if we can somehow minimize, if we can somehow find a q dot that minimizes this least square, then that could be considered as a least square solution for the variable q dot. So the procedure is as follows. We have basically defined our objective, and hence we set up our objective function as such. So this is nothing but like least square is simply like if we are given a vector, x and y, the norm of it is nothing but x square plus y square. This is nothing but xy transpose xy, right? If you multiply these two vectors, it'll be x square plus y square. So again, that is what we are defined in the following step. So the norm of mu minus j of q times q dot would be nothing but mu dot minus j of q times q dot transpose mu dot minus j of q times q dot. And this is a scalar equation, right? This is a single scalar equation because mu dot minus j of q times q dot, for example, could be a 3 cross 1, a tall vector. So taking the transpose, it could be 1 cross 3, and this could be 3 cross 1. So the total order would be 1 cross 1. So this is a scalar equation. And we want to minimize this objective function with respect to the variable q dot, because that is what we want to find a solution of q dot that would make this objective function minimal. So taking the partial derivative of L with respect to q dot and equating it to 0, this would be nothing but there is a 2 also, because this is nothing but a square. So taking that 2 outside, it would be something square derivative of something square would be, for example, if this is nothing but dou by dou x of x square, you will have 2x, right? So that's all this derivative is all about. So you have this thing mu dot minus j of q times q dot transpose. Then we also need to write out the coefficient of q dot. That will also come out as due to the fact that we are taking the partial derivative of it. So you'll also have a term j of q, and there is a minus sign here also, so we'll also have a minus sign. right? So like simply rearranging this equation, we take this this negative mu dot times j of q in one side of this equation, and the remaining to the other side of the equation. So on expanding, it will be like mu dot transpose j of q would be equal to q dot transpose j of q transpose j of q, right? So we are simply expanding this transpose. So this term would be j of q times q, the whole transpose. So this would be q dot transpose j of q transpose. Then this j of q will come over here. We'll have j of q, right? This is nothing but a b the whole transpose. This would be b transpose a transpose. So we are simply expanding this transpose. That's all. So again, if we are taking the transpose again for on both of the sides for LHS as well as RHS, so this would be A and this would be B. So again, if you're taking the transpose, it would be B transpose A transpose. So we'll have J of Q transpose mu dot of T transpose. The whole transpose would be simply mu dot. And we are also taking the transpose of this entire RHS, right? So it would be J of Q transpose J of Q times Q dot. And again, further manipulating, we are taking this entire term to this side. How do we do that? We take this entire term and multiply with this inverse, and apply pre-multiply both of this equation with the inverse. So it will be J of Q transpose J of Q, the whole inverse. We also do the same thing over here, so that the inverse and the main term would get cancelled. So in the end, we would end up with this expression. So what we have obtained here is the least square solution of Q dot, right? So like unlike the case of a square matrix, in case of a square matrix, it was simply Q dot would be J of Q inverse mu dot. But for an overdetermined system, we have an approximate solution that minimizes the least square. And for the overdetermined cases, this is what our final equation would be. And we have something, this term is equivalent to the inverse of a square matrix. We call this term as a pseudo inverse. So this term, J of Q transpose J of Q, the whole inverse J of Q transpose. We would call this term as a pseudo inverse. So Q dot would be J of Q pseudo inverse mu dot. And for this condition to exist, for this pseudo inverse to exist, J of Q transpose J of Q, the determinant of this thing should not be equal to 0. Because like we again have an inverse, like this matrix, whatever we have in this bracket of this inverse, this would be square. You can, if you multiply this non-square J of Q transpose times J of Q, this would be square. And for this inverse to exist, the determinant of J of Q transpose J of Q should not be equal to 0. Because as you know, a determinant of a matrix, sorry, inverse of a matrix is adjoint of A by determinant of A. And in order for this to exist, the determinant of A should not be 0. And the same reasoning can be said for this term. The determinant of J of Q transpose J of Q should not vanish. So yeah, for this case, like this entire expression is called the left inverse, left pseudo inverse for the case of m greater than n. This entire expression is called the left pseudo inverse. Okay, so we have one more case when the number of equations is less than the number of unknowns. So when the number of equations are less than the number of unknowns. So we would end up with a a short and a broad matrix, something like this. So m by n, and here the m is less than n. So when the number of equations is less than the number of unknowns, and if you could end up with infinite number of solutions, because no matter what sort of variables you use, like if you basically choose the null space of this matrix, you could theoretically find infinite number of solutions. It all depends on whether the equations are dependent or independent. Maybe it does not even matter. But you can have multiple number of solutions, or in fact infinite number of solutions, when the system is underspecified. You will have fewer equations than the unknowns. So as a result, it can have multiple number of solutions. And if that is the case, we would prefer to pick the solution having the minimal norm. So if we have multiple solutions, q dot, for example, q dot, the yeah, for the problem of q dot would be j of q inverse mu dot, where in the j of q is a short and a broad matrix where m is less than n. Q dot can have many solutions, many number of solutions. And out of all these solutions, you would pick some solution which is having minimal norm. So I suppose you know what norm means. So if you have a vector q dot comprising of elements q1, q2, q3 dots, second norm or a two norm would, the two norm is nothing but q1 dot square plus q1 q2 dot square plus q3 dot square is nothing but the length of this vector. And it doesn't matter the number of elements of the vector, it is nothing but the length of the vector. q1 dot square plus q2 dot square plus q3 dot square, the whole under square root. And you can also think in this way, a minimum norm in the sense the length of this vector would be minimum, or in that case, the effort you would need to give into the motors would have minimal norm compared to all the other solutions. So I suppose you can understand why we go for this minimal norm, because the effort at which you would put. Okay, I got a question. So it's from Parimal Sami. It says, when the system is over specified, we will only get an approximate solution. Can you, okay, can you give some examples of these types of manipulators? At the top of my head, I cannot think of any manipulators that would require, but there are cases, because as I've told you earlier, there are cases of redundant robotic manipulators, right? So if there are more number of joints, q3 dot, and if x and y are the only positions to be controlled, you will end up with something, a tall matrix. Sorry, I guess this is that the correct case? If there are more number of unknowns over specified systems, x, y, z, theta 1 dot, theta 2 dot. No, at the top of my head, I cannot basically recall any manipulators, but you can effectively control 3 positions using 2 motors, but you may not even get the required orientation. It can achieve all the 3 positions, but it cannot it cannot achieve in however way you basically want. Like within this short, this is just an example, but you would need to go to higher orders, not with just 2 actuators, but maybe if you go with 4 or 5 actuators, there could be cases where the system would be overspecified. Like you will basically try to control more number of freedoms than the number of controllable inputs that you can have. Such cases may arise at higher orders. Yeah. But at the top of my head, I cannot give you an example of such robotic manipulators. But if I can come across, I can share that through the discussion forums. All right. Yeah. So I hope regarding the underdetermined cases where the number of unknowns are, the number of equations is less than the number of unknowns, you would probably prefer a minimal norm solution. So minimal norm is where the norm of the solution vector is minimum. So in other words, the effort, the inputs that you would give the actuators, it will have minimum norm compared to all the other solutions to achieve the same end effector velocities or to achieve the same task space variables. So in that regard, the minimal norm, you can, in one way, based on the norm, you can basically say that it requires the least effort to be inputted into the joints of the robot so that we can achieve the same end effector velocities. So the problem is to find out the solution, the correct solution of q dot that satisfies this constraint equation, mu dot minus j of q equal to 0, such that, so, and also we have to ensure that q dot is of minimal norm. So this is basically norm of q dot, and we basically want to minimize it. So our objective function would something like this. So q dot transpose q. So this is the norm of q, right? We want to minimize the norm of q such that it would satisfy this constraint equation. So this is our typical constraint velocity constraint equation. Mu dot minus j of q times q dot. Mu dot should be equal to j of q times q dot, and mu dot minus j of q times q dot equal to 0. So these are our constraint equations. So like for any optimization problems, so like for plenty of optimization problems, you would come across this specific format. Like minimize something subjected to some constraints. This is a common format, and the parameter lambda is nothing but weights that you would give to each of the constraints. And this is nothing but, this is what we call Lagrange multipliers. So this is something, this is basically a typical problem of optimization, minimizing an objective function subjected to some constraints. So we have essentially two variables to be minimized: lambda, the variable lambda, which is the Lagrange multipliers, and we also have this q, where we would want to minimize the q as well. We would want to minimize this entire function on lambda as well as the vector q dot. So in order for you to do that, you first take the partial derivative of this objective function with respect to q dot. You would end up with this expression. So this is q dot square. So taking partial differentiative, you will end up with 2 times q dot transpose. Right? The transpose basically means it is a scalar equation. This is nothing but a 1 cross 3. If you take the transpose, this would become a 1 cross 3 expression. And further, you again partially differentiate this term with respect to q dot. So this term basically vanishes because this does not have any terms in q dot. And only this term remains. So if you take the partial derivative, you will, the remaining terms would be lambda transpose times j of q. So that is what we have over here. And again, since we have to minimize this problem with respect to lambda as well, we take the partial derivative of L with respect to lambda also. So that would yield you, taking partial derivative of this entire expression with respect to lambda would leave you this expression. Right? Because this term with respect to lambda is virtually 0 because there is no lambda term. And partial derivative of this term with respect to lambda gets cancelled out, you will end up with this term. So that is what we have over here. Right? So from this first equation, from equation 7a, we write q dot in terms of lambda. This is basically a standard procedure. So writing q dot in terms of lambda, we end up with this expression over here. Right? We have q dot transpose here. So first you take first you move this term to this other side of this equation, then take the transpose in both LHS and RHS, and further rearranging, you would end up with this expression. Right? And substituting this new expression, whatever we have obtained from equation 7a as 8, if you substitute the value of q dot into equation 7b, so q dot into 7b, you will get an expression of mu dot. So take this negative term onto the other side and substitute q dot using equation 8, you would end up with this equation. So mu dot would be j of q times j of q transpose lambda, the whole divided by 2. And again, on further substituting this entire expression back into equation 7a, right? So essentially what you're doing is that you find the expression of lambda from this equation, right? So you can take 2 over this side and multiply this entire thing, j of q times j of q inverse to this side, you will end up with this equation. So from equation 9, find lambda in terms of mu dot, you would end up with this equation. And again, substituting this lambda onto this equation 7a, right? Lambda in terms of equation, this equation, you would end up with the final solution as such. So this is the minimal norm solution of an underdetermined system, where the term over here, this term, is called a right pseudo inverse. This is also again a pseudo inverse. J of q transpose J of q transpose the whole inverse. This is something called a right pseudo inverse. And now q dot can be written as the right pseudo inverse times mu dot. And in order for the right pseudo inverse to exist, the determinant of j of q times j of q transpose should not vanish. Because in order for this inverse to exist, this determinant should not vanish. Right? So that is about the case of pseudo inverses, when the number of rows and number of columns are not equal, or in other case, the number of equations and number of unknowns are not equal. Like if in case of an overdetermined system, we would go for this approximate solution by minimizing the least squares. In case of an underdetermined system, we would prefer to pick out the solution having the minimal norm out of all the available solutions. Okay, I'm again getting a doubt. It says lambda is a scalar, but no. Lambda is not a scalar. Lambda is actually a vector, because it is a weighted parameter. You would give lambda will have equal number of parameters as the number of parameters you would have in Q as well. Right? Is that clear? The Lagrange parameter, like in this case, if Q dot is Q1, Q2, Q3 dot, lambda would also be of the same order, lambda 1, lambda 2. Lambda. It has weights also. Is that clear? Okay, yeah. It also is a vector. Okay, then we also dealt with a velocity propagation model in the lectures. So in the previous lectures, in the previous weeks, we have basically come across a general transformation motion. So for example, like if we have 2 frames of references, so I'll call this X, Y, Z. Let this be a frame A. We have a rotating frame over here, B. Let this be XB, YB, ZB. Right? And we also have a vector attached to the frame B. We can call this as the vector P. Right? So if you want to express the position of the position vector, okay, let this be Q, like to be consistent with the terminologies. We have a vector Q that is attached to the frame B. So the position vector of Q with respect to A, right? So we have position vector of this point Q with respect to A is position vector of B, the frame of reference at which the Q is attached, position vector of B with respect to A, position vector of B with respect to A, plus the relative position of Q with respect to B, position vector of Q with respect to B. Right? But since we are expressing all these terms in terms of the frame of reference A, but this is only in terms of frame of reference B. So if we want to express this in frame of reference A, we would also have to pre-multiply this with the rotation matrix B with respect to A. Right? Because this is a rotating frame of reference. B is a rotating frame of reference, and the rotation of B with respect to A is mapped using this rotation matrix. And due to the fact that B, the point Q is firmly attached to the frame of reference B, you would have to pre-multiply this with respect to the position of Q with respect to B. Right. When it comes to velocities, you would differentiate this entire expression. You differentiate this entire expression in order for you to get the derivative of position vectors. Right. So what will you get if you're differentiating this? So if you're differentiating this term, you would get this term. It's a simple derivative. And differentiating this term with respect to time, you would get this term. And on applying chain rule, you would get these two terms. Right? So derivative of Q with respect to B, if we take the time derivative of this term, applying chain rule, we will get the first term multiplied by the derivative of the second term plus the derivative of the first term multiplied by second term. So this is what we end up. Applying the chain rule, we'll end up with the second and third terms. Okay. So again, there is also a thing to notice. We also have the derivative of this rotation matrix coming up. So if you can recall the lectures, we have established in the lectures that the derivative of the rotation matrix is nothing but omega cross r. Omega is the angular velocity at which the frame of reference B would be rotating with respect to the fixed frame of reference. And this term, derivative of r, is nothing but omega cross r. Right? The easiest thing is that, as you know, the rotation matrix R is nothing but R transpose, right? It's an orthonormal matrix. So R times R transpose is identity matrix. Because we have actually seen that the rotation matrix is orthonormal. So if you take the derivative of this equation, it will be R dot R transpose plus R dot transpose. So derivative of identity matrix is nothing but 0. So you can also rewrite this expression as R dot R transpose plus R dot R transpose, the whole transpose. Right? So if you expand this big term, you will end up with this term. There is nothing wrong in writing this term. Right? So this is a matrix R dot R transpose. So if I write R dot R transpose as a matrix, then what does this equation tell you? So if R dot R transpose is a matrix, then S plus S transpose is 0. A matrix plus its transpose is 0. So when can that happen? That can only happen when this matrix R, that can only happen when this matrix S is Q-symmetric. Right? A skew-symmetric matrix added with its own transpose is 0. And what is this S? S is nothing but R dot R transpose. R dot R transpose is a skew symmetric matrix, right? And yeah, that is what it basically says. So the derivative of R dot. So if you know that this R dot R transpose is a skew symmetric matrix, then what is R dot? So R dot would be, if you are taking R transpose over to the other side, it would be R times S. R dot would be R times S. Sorry, yeah, 1 second. I'll just rewrite this. I hope I'm not confusing you. If you are confused or if it is hard to follow, please let me know. You could unmute yourself and ask me to repeat again. That is not a problem. So I'm simply multiplying this equation, post multiplying this equation with R. So then what will happen? R dot R transpose R would be SR. I'm simply multiplying both of the sides with R. And since R is an orthogonal matrix, this would be an identity matrix. So this R dot would be S cross S times R. And what is this S? This S is nothing but a skew symmetric matrix of this form. So as you know, skew symmetric matrix will have all its diagonal terms as 0. Then the remaining terms would be omega x minus omega y, omega z, then the transpose of it, which would be minus omega z, omega y, omega x. Right? So if your frame of reference in concern, if the frame of reference B is rotating with angular velocities of components, omega x, omega y, omega z, this term R dot would be nothing but S times R, where S is this matrix and R is already what you have. Right? So yeah, this omega, like it, you should also know that you can write a cross product, omega cross R. This is nothing but a cross product. You can write any cross product as a multiplication of matrices and vectors, right? So for example, if omega is omega x, omega y, omega z, and R is Rx, Ry, Rz, these two equations, the following two equations are equivalent. So omega cross R, right? You can write this, or you can write this same expression as some omega vector multiplied by this R vector, where this omega matrix would be this thing. It's the same thing actually. Omega x minus omega y, omega z minus omega z, omega y, omega x. And R would be Rx, Ry, Rs. So like whatever you get using by taking the cross product of omega cross R, you can get the same result by doing this matrix multiplication. These are basically identical. Omega cross R and this matrix, skew symmetric matrix omega times this vector R, both are basically the same. And that is what this expression also says. This R dot is omega cross R, right? Cross product, or this big matrix, the skew symmetric matrix multiplied by the matrix R, whatever you have over here. Both are basically identical. Both relations are nothing but identical. So that is how you get this R dot as omega cross product R, then the remaining term, position vector of Q with respect to B. Right? Then using these principles, we have also come across the velocity propagations. So velocity propagation in the sense, like for example, if we have a robotic arm with multiple joints, for example, in the context of an RR robot, a 2R manipulator. So this would be R1, this would be R2. So the velocity propagation basically means, like, if you are given the velocity of the base, so typically the angular velocity of the base would be considered to be 0. And if you are also given the velocities of each of these joints, R1, R2, then what would be the subsequent velocities of, what would be the subsequent angular velocities of all the joints? So you can use these recurrence relations, these iterative solutions, so that you can identify the angular velocities of the upcoming joints or the successive joints. So this basically deals with the angular velocity propagation models. Angular velocity propagation models for two cases, for rotary joints as well as prismatic joints, right? So this is nothing but the angular velocities of the I+1 ring, I+1 link is the angular velocities of the previous link or the preceding link plus the joint velocity of the current link. It's not that hard because, for example, if you can consider two links, so let this be link I. We have a joint over here. Let this be the I+1 link. This is I+1. This is link I. This is link I+1. And this is a rotary joint. And as you can recall, the rotary joint will have the Z axis orthogonal, parallel to the axis of the joint. So this is Z I+1. And this link, this entire link can rotate about this axis, Z axis. Right? So this expression basically says the angular velocity of link I+1. So if this is link I+1, right? So the angular velocity of this link omega I+1, we also have the angular velocity of link I as omega I. So the basic expression is angular velocity of link I+1 is angular velocity of link I plus the contribution by this rotation. Since link I+1 is rotating with respect to link I, because we have a revolute joint over here, and the revolute joint basically rotates by an amount theta dot I+1. So we write as 0, 0, theta I+1 dot. Because since by the DH convention itself, the Z axis is always aligned with respect to the rotational axis, and the angular velocity of link I with respect to, the angular velocity of link I+1 with respect to link I would be some units along Z I+1. So that is this term, theta I dot, the theta dot I+1. And like this expression is basically valid for all the frames, but we prefer to write this expression in terms of the frame that is attached to the link I+1. Because we are dealing with the angular velocity of link I+1, we would like to express this entire equation in terms of the I+1 frame. Because as you can recall from the DH convention, the I+1 frame is attached to the I+1 link. Right? If you want to express this entire equation in terms of I+1 frame, this is expressed with respect to ith frame. Angular velocity of I, the previous link is expressed with respect to its own link. So we need to transpose it to the current frame of reference, that is I+1. So how do you do that? If you want to do that, you multiply this with the appropriate rotation matrix, that is I+1. right? The rotation matrix of I with respect to I plus 1 multiplied by omega I. So omega is expressed with respect to its own frame of reference. Then we have the 0, 0, theta I plus 1 dot. And we don't need to multiply any rotation matrix because it is already expressed with respect to Zi plus 1. It's already expressed with respect to Zi plus 1. So that is what this relation is all about, right? So this can basically begin all the way from I is 0. So I is 0 all the way to I equals n, right? Because I is 0 means the fixed base. So for fixed base, I is 0. So if you are given an angular velocity of the fixed base, so for example, in most of the cases, the angular velocity of the fixed base would be given as 0. So 0 omega 0 would be 0, 0, 0 because the fixed base is always going to be fixed. And you would also be given the angular velocity of link 1, sorry, the rotation of link 1 with respect to link 0. This vector would also be given, sorry. This vector would also be given. You would have to find out this vector. So these are all knowns. This is the unknown. So what you do? 1 omega 1 would be that would be 1 r0 0 omega 0 plus 0 0 theta 1 dot. So you would be able to figure out the angular velocity of link 1. Now that you have obtained angular velocity of link 1, you can propagate it further. So if that is the case, then further propagation would yield you 2 omega 2 would be 2r1 1 omega 1 plus 0 0 theta 2 dot. Because we have already obtained this from the previous step, this will be given. So if that is the case, we can, using the propagation model, using this propagation model, we'll be able to find 2 omega 2. And subsequently, we will be able to reach all the way up to the nth link. Right? That is about the rotary joint. And what about the prismatic joint? So in case of a prismatic joint does not have this component. Right? Prismatic joint basically translates. So the I plus 1 link of a prismatic joint translates with respect to the ith link. It does not rotate. It does not have an angular component. So this term does not exist for a prismatic joint. Right? So the angular velocity of the current link is the angular velocity of the previous link, but it is only brought forward to the I plus 1th frame using this transformation matrix, rotation matrix R. That's all. This term basically vanishes because it's a prismatic joint. So this is about the velocity propagation model of angular velocity propagation models of rotary as well as prismatic joints. Whereas you also have a linear velocity propagation model also for both rotary and prismatic joints, right? So how do you do that? So the general expression is the velocity of the current link, velocity of the I plus 1th link is the velocity of the previous link, ith link, plus omega cross the centrifugal component, omega cross I plus 1. Sorry. Omega I cross P I plus 1 to I. Where this vector, the position vector of I plus 1 with respect to P. So if we have a link like this is the ith frame and this is the I plus 1th frame. This distance is nothing but this vector, the position vector of I plus 1 with respect to I. And if you want to bring this entire thing into a common frame of reference, that is with respect to I plus 1, we pre-multiply this entire expression using this rotation matrix. So to bring the frame of reference from I to I plus 1, we are pre-multiply with this specific rotation matrix. Because everything else in this bracket is with respect to ith frame, right? Everything within that bracket is certain with respect to ith frame. We want everything to be brought into I plus 1 frame. So we rotate it with the appropriate rotation matrix, right? And this is for the rotary joint. And in case of a prismatic joint, we have all of these components plus one more additional term, that is 0, 0, di plus 1. Because for prismatic joint, we have an ith link, link I. We also have a link I plus 1, link I plus 1. And there is a relative velocity between link and I plus 1 in the linear direction, di plus 1 dot, because this is a prismatic joint. So taking that into consideration, we have the velocity of the ith link, y plus 1th link, expressed with respect to the I plus 1th frame as this expression. I hope this is clear enough. So like in the lectures, we have also come across the terms. We have something called the slip velocity. We have also called the centripetal velocity. We have also something called the relative velocity. All these terms will also have these terms. And it can get even more involved in acceleration. Like if once you go to the dynamics, you will further have to differentiate this term with respect to time. So you will have even more terms, even more number of terms. Right. Okay. So yeah, coming on to the last topic on this session, we'll deal with something called statics. So statics is the problem of finding out the correct joint forces, the correct forces to be applied at the joints so that the manipulator will maintain static equilibrium. So for example, if you have a 2R manipulator like this, comprising of two revolute joints, right? And the robot manipulator is subjected to some external forces. Maybe it can have some external forces on its end effector. It can have some external forces at anywhere on the link, maybe due to its gravity, maybe some external forces, right? And in order for the robot to remain in static equilibrium, what are the torques that you should apply on each of these joints? Right? In order for the robot to maintain static equilibrium despite these external forces on the end effector as well as any other part of the links, what torques should you give onto the joint so that the robot would maintain static equilibrium? Right? The conditions for static equilibrium are the sum of all the forces acting on a link should be 0, and sum of all the moments acting on a link should also be 0. Right? So that can be identified using the free body analysis of each of these links. So if you consider a link, all right? So if this is link I, and each of this link I will be attached with a frame of reference. Again, that is I as well. So this would be Xi, this would be, sorry, let this be Zi, let this be Xi, let this be Yi, and let this be the ith frame of reference, right? And each of these links would be subjected to external forces. You can have forces, acting over here, that is acting on this frame of reference, that is F of I with respect to I. You can also have forces that is coming from the following link, the link that is further attached on this link to this link, further forward. So you can have reaction forces because of the following link, that is the forces Fi plus 1 with respect to I. You can also have moments because of the other links, that should be the moment Ni plus 1. You can also have moments due to the previous links also, that is Ni. All these forces are there. So if you take the free body diagram and if you solve for the static equilibrium conditions, you will end up with these equations. So the sum of all the forces should be 0. So taking the negative components to the other side, you will end up with this equation. The forces acting on the ith frame should be equal to the forces acting on the I plus 1th frame, right? And the moments acting on the ith frame should be equal to the moments acting on the distal part of the link, and also due to the moment caused by the force. So you also have a force over here, Fi plus 1, and there is a distance also, the link length. So this force will also create a moment on this joint because of this moment R, the moment arm caused by the link length. So that is this component. And expressing this entire static equilibrium condition in a single frame, with respect to a single frame, you will have to pre-multiply these expressions with appropriate rotation matrices. Because that is the purpose of making it recursive, because you have the force I, the forces acting on I, that is defined with respect to the ith frame. We also have the forces acting on the I plus 1th frame, that is referred with respect to the I plus 1th frame. And we would want to bring everything onto the ith frame. So you pre-multiply this with the appropriate rotation matrix, because everything should be expressed with respect to the ith frame. So since this is in I plus 1th frame, by pre-multiplying the appropriate rotation matrix, we can bring everything back to the ith frame. So the similar case over here also. So we have the moment acting on the I plus 1th frame. We have to bring it to the ith frame using this rotation matrix. And this term is already expressed with respect to the ith frame. We have a subscript over here I. We also have the forces acting on I. Right? So no need to multiply the rotation matrix, but this is the general point of it. Right? The important thing is, first you write this equation, don't bother about the frame of reference, then convert it back to the appropriate frame of references using the appropriate rotation matrices. Just like what we did with the velocities also. Okay, so again, just like in the case of velocities, we would also need to transform between different frames of reference. We would also need to transform the forces and torques between the task space and the joint space. So how to do that? So like simply by employing the principle of conservation of power, it's nothing but the power on the configuration space, or power to move the robot on task space, is equal to the power to move the robot on operational space. So it does not matter on which coordinates you specify. The power acting on power is basically conserved. It should be constant whether you represent the power in configuration space or whether you represent the power on task space. Sorry, task space or in joint space. So the expression of power is nothing but the force or the wrench times velocity, right? Power is nothing but force times velocity. And this expression is written in joint space and this is written in task space, where tau is the wrench in joint space, q dot is the velocities in joint space, f is the wrenches in the task space, mu dot is the velocity vector in task space, right? So again, like as you might know, taking the dot product is nothing but taking the transpose. Like all these vectors are 3 cross 1, right? All these vectors are 3 cross 1. So taking the dot product, taking the transpose and multiplying, you will end up with 1 cross 3 times 3 cross 1. You will end up with the 1 cross 1 scalar. Because at the end of a dot product, you will get a scalar. The same operation can be replicated using the transpose also. You would again get a scalar. And if you know what this mu dot is, we know mu dot is J of Q times Q dot, right? this term. So substituting j of q times q dot in instead of mu dot and rearranging it, if you are taking the transpose of this entire equation, just by taking the transpose, it would be like, yeah. Before that, we can basically cancel this q dot and q dot, all right? And taking the transpose of both LHS and RHS, you would end up with tau would be J transpose F. That is what this expression is. So in order to transform the coordinates of the wrench acting on the dart space and the joint space, we would again have to employ the Jacobian, right? So earlier for the transformation between velocities, we used Jacobian. Here for the transformation of wrenches also, we are using the Jacobian. So that is also another potential usage of Jacobian, right? In the case of, if you want to make the robot in static equilibrium for when it is subject to a specific set of forces, what are the torques that you should apply on the robot? You can estimate this torque by using this Jacobian matrix if this force vector is known, right? Yeah. Okay, then we also have a topic of singularity. So again, this is one of the potential analysis where the Jacobian matrix will get involved, right? So going through the definition, it says in singular configurations, the number of degree of freedom of the end effector is inferior to the dimension in which it generally operates, right? And singular configuration can happen when the two axes of prismatic joints become parallel, the two axes of revolute joints become identical. So like if you have a multi-axis robotic arm, maybe of 6-axis robotic arm, if the two revolute joints basically align, it will essentially lose a degrees of freedom, because if you rotate one of the aligned revolute joint, you will get one motion. If you rotate the other revolute joint, you will get the same motion. So you are using the two different inputs to get the same motion. But originally, it was intended for getting two different motions. But since they have become parallel, the two inputs can only give a single output. So that is the peculiarity of these singular configurations, right? The robot basically loses one of its degrees of freedom, one of its intended degrees of freedom. And these are the general cases where such singularity configurations can happen, right? And coming on to the further points, it says at singular positions, the end effector loses one or more degree of freedom as the kinematic equations become linearly dependent. So like, as you can see, like the kinematic equations can be written in terms of the forward kinematic expression. Mu dot would be J of Q times Q dot. And if, as you can recall from the concepts of linear algebra, when the kinematic equations become linearly dependent, the rank of the Jacobian matrix decreases from the full rank. Or in other words, determinant of J of Q becomes 0 when the robot is at singular positions, because the equations becomes linearly dependent, right? And because of this fact, the singular configurations must be avoided, as velocities required to move the end effector becomes theoretically infinite. So this is a rather an unfortunate or an undesirable phenomenon. We would want the robotic manipulator to avoid singular configurations, as it can confuse it could possibly confuse the controller. It would basically say you have to move in infinite velocities to move in a specific direction, right? Just like I have explained in the case of an RR manipulator. For example, if all the links of an RR manipulators are aligned like so, and if you're trying to get an end effector velocity along this axis, can you move that? Can you do that? It's not possible, right? You cannot move in this direction. You can only have an angular velocity perpendicular to this thing. You cannot have an angular velocity along this component because the resistance is virtually infinite. But if you give a command to the robot at this configuration that you want to move along this direction, the controller will give you have to move with infinite velocity. You have to give infinite velocities so that in order for you to move along this direction. So that should be avoided. Singular configurations is something that is to be avoided. Okay, so coming to the different types of singularities, we have in a broader classification, we have two different kinds of singularities. One is called the workspace singularities. So these basically occurs at the boundary of the workspace. Like when the robotic arm is fully stretched, it cannot go further beyond, right? For example, in the case of an RR robot, if the robot is fully stretched like this, it cannot have a velocity in this direction as well as in this direction because it will have infinite resistance. So those kinds of singularities are called workspace boundary singularities. So these mostly happen at the extreme ends of the workspace. And we also have something called interior singularities. So even the robot is within the workspace, not at the extreme ends, it can still encounter this singular configuration. So generally, in this case, is the axis two or more axes of the robot lines up, right? So if you have a multi-axis robot, if the two revolute joints lines up, right? If you have two revolute joints, like for example, this may not be the case. These are the axes of the revolute joint. So this is Z2, this is Z1, and let this be an end effector. So if you rotate this revolute joint, or if you rotate this revolute joint, you would get the same result, right? You would get the same angular velocity of the end effector. That happens when the axes of the revolute joints line up. But if they were in different directions, maybe one along this direction and another along this direction, this case would not have happened. But these scenarios can happen. Like these need not be adjacent links. These need not be adjacent revolute joints as depicted in this figure. This is just an example. There could be a numerous different other joints in between. But at singular configurations, any two revolute joints can align. And due to this fact, it can basically lose 1 degree of freedom because both of them would rotating, either of them would give you the same result. Right? So that is about interior singularities. Yeah, and now we would solve a few questions regarding week 4. This is more or less similar to what you can expect for this tutorials, for the assignments of week 4. Yeah, and the first question it says, for a non-square matrix Jacobian with linearly independent columns, the Moore-Penrose inverse can be written as, what is the correct answer? So a non-square matrix with linearly independent columns, that means it has more number of rows than more number of columns. Linearly independent in the sense like it has just the required number of columns. Sorry, just the required number of columns. So it could have more number of equations. So if this is an M cross N Jacobian matrix, M can be greater than N. Because it says linearly independent columns, it only has just the number of columns so that they are independent. If you're adding any more number of columns, it would be a linear combination of the independent columns. Right? If that is the case, then what is the Moore-Penrose inverse? So Saurav has said option 2, that is J transpose J, the whole inverse J transpose. And I agree with that because if you have more number of rows where m greater than n means more number of equations than unknowns, then the system is overdetermined, and as such we would go for the solution that has the approximate solution, approximate least square solution. And the approximate least square solution is given by the left inverse. As you can recall, q dot would be j transpose j, the whole inverse, j transpose mu dot. This is the approximate least square solution for an overdetermined system. And the question basically asks the Moore-Penrose inverse for this specific case. And in that regard, the correct answer is the left inverse. So if you check the answer, that is indeed the correct answer, right? We have discussed this in the beginning of this session. Okay, so moving on, again, this is a question related to the previous question. It says, for a Jacobian matrix with linear independent columns, its pseudo-inverse exists if and only if. So we have already established that linear independent columns means it is an overdetermined system and the approximate least square solution is given by the left inverse again. That is, what was that? J of J transpose Q times J of Q, the whole inverse, J transpose Q, mu dot. Right? Yeah, again, I have received the option as option 1 from Saurav. Right? So this is the left pseudo inverse, and in order for this pseudo inverse to exist, this inverse J of Q, J of Q, J of Q transpose J of Q, in order for this to exist, the determinant of J transpose J should not be equal to 0. Because for an inverse to exist, it should not be singular. Adjoined by determinant, adjoined A by determinant A. So determinant should not vanish. So that is what this condition essentially says. So again, like, I think it's fairly straightforward. I'm getting the answer. So it's option A itself, the right answer. Okay, moving on to question 3. It says the linear velocity propagation model of a prismatic joint is given as. What is the linear velocity propagation model? It can look a bit intimidating at first, but if you can grasp the concept, it's fairly straightforward, right? Because in order for you to propagate it to the next link, the velocity of the I+1th link is the velocity of the ith link, right? The ith frame, plus you will also have this centrifugal term, omega cross P, omega cross R. So this is the link length. So the link length starting from the ith frame to the I+1 frame. And due to the fact that this is a prismatic joint, the velocity of the I+1 frame will also be contributed by the linear displacement theta d I+1 dot as well. Right? So again, like, in order for it to be recursive, the velocity of I will be represented with respect to velocity of ith frame, and omega of I also will be represented with respect to the ith frame again. And yeah, one second. The distance from the ith frame to the I plus 1 frame will also be represented with respect to the ith frame again. This would be I plus 1 with respect to I. But in order for it to be recursive, we would like to have everything with respect to the I plus 1 frame. So how do you do that? You pre-multiply the terms, all the terms that is in the ith frame. So this term is in the ith frame, this term is in the ith frame, this is also in the ith frame, but this is expressed with respect to the I plus 1 frame. Because this basically corresponds to the linear velocity of the I plus 1 frame. So that is expressed with respect to I plus 1 frame by default. And all the terms that is remaining on the ith frame, we transpose it to the I plus 1 frame using the rotation matrix. Rotation matrix that transpose it from ith frame to I plus 1 frame. Right? So here, what is the correct answer? Again, I have received the option as 2. Is it correct? Yeah, the ith velocity of ith frame, the radial component plus this component. That is indeed correct. Because all the other options, it can it basically have the rotation matrices mixed up. This is not wrong. We are representing the distance from ith frame to I plus 1 frames, not the other way around. So this is wrong. And in this case, the second option is correct. The third option, the rotation matrix indices are mixed up. The fourth option also has the same issue. Fifth option also has the same issue. And in the case of sixth option, yeah, this is not DI, this is DI plus 1. That is the issue. Okay, so I also agree that the correct option is option B or option 2. That is indeed the correct answer. Yes, moving on to question 4. It says, this is an elementary question. It says, the work is the cross product of force and torque vector and a displacement or an angular velocity vector. Right? So work, it says it is a cross product of force cross some displacement vector. Is this correct or not? So work is a scalar quantity, right? Work is nothing but the dot product of force and displacement. But it is not a vector quantity. Yes, that is indeed false. Yes. Okay, moving on to question 5. It says the singularity or singular positions of a serial manipulator can be found by solving dash. Which of the options is correct? J is the Jacobian matrix, and for simplicity, it is assumed to be a square matrix. Right? So we have this configuration, the forward kinematic equation, mu dot would be J of Q times Q dot. And to see how can you find the singular positions of the robotic manipulator? Singularity or singular positions of the robotic manipulator can be found by solving which of the following conditions? Is it option? Yeah, I got the option as option 2, determinant of J as 0. Yes, that is indeed correct. Because as we have seen, when the determinant of Jacobian is 0, that means that the robot is in singular configuration. You can actually try this using an example on your own. If you can assemble a Jacobian matrix of a 2R robot, right? It will be a 2 by 2 Jacobian matrix, J11, J12, J21, J22. And if you take the determinant of this Jacobian matrix, you will be able to find out the conditions, theta 1 and theta 2. The conditions for theta 1 and theta 2, where the robot becomes singular. So just by solving this determinant, you will be able to get the conditions of theta 1 and theta 2. So I agree with that. Option 2 is the correct answer. Let us check the answer key. That is indeed the correct answer. So like, please let me know, like we have a limited time left. If I'm rushing through the questions, please let me know. I'm happy to explain. Oh, okay. So we have that same problem, the problem that I have discussed earlier. It says, for an RR manipulator, find the linear velocity vector of the end effector with respect to the base frame. So like the proper way to do is the velocity propagation. Like you can use this velocity propagation law, like Vi plus 1 is Vi plus omega I cross I plus 1. Sorry. Yeah. Omega I. This is basically the right way of doing that. And we also have this I plus 1 I plus 1. You could basically do this to find out the angular velocities. You basically begin from the zeroth frame, right? We have a zeroth frame over here, and we go all the way up to the third frame using this recursive relations. But is there a need of this? Because for simple manipulators, maybe for up to 3 degrees of freedom robot, you don't have to use this expression. You can directly write the velocity equations by the simply from the geometry of the robot, right? You can use this because you cannot do that for spatial three-dimensional six-axis robots. That is not that cannot be easily done. But for manipulators in planar manipulators, lower degrees of freedom planar manipulators, you can directly write out the kinematic expression, right? For example, you can write the x if x and y are the end effector positions. You can directly write down what is the x coordinate of the end effector. That is nothing but L1 cos theta 1 plus L2 cos theta 1 plus theta 2, right? Because this angle is theta 1 and this entire angle is theta 1 plus theta 2. And similarly, y would be L1 sine theta 1 plus L2 sine theta 1 plus theta 2. And to find out the velocity, you simply have to differentiate this with respect to time. So x dot would be minus L1 sine theta 1 dot. Then what else do we have? Minus L2 cos theta 1 plus theta 2 times theta 1 dot plus theta 2 dot. And y dot would be L1 cos theta 1 dot plus L2 cos theta 2, sorry, L2 cos theta 1 plus theta 2 multiplied by theta 1 dot plus theta 2 dot. So these are the expressions for velocities of the end effector, right? So from that, what would be the correct answer? The correct answer is nothing but, I suppose, did I make a mistake? Because this is not cos, this is again sine, right? So which of the option is correct? I'm not getting any answers. I suppose option B is correct, right? L1 theta 1 dot. Yes. Yes, I guess this is correct. I hope you can all agree with that. Yes, option B is indeed correct. Okay, moving on to question 7. It says for a given RP manipulator, the forward kinematic solution is given as x is d2 cos theta 1, y is d2 sin theta 1. Find the Jacobian matrix of the end effector with respect to the base frame, considering only x and y. So we can basically solve this expression for the Jacobian matrix, right? So as you might know, the expression, the forward differential kinematic expression is mu dot is J of Q times Q dot. So what is mu dot? Mu dot is x dot, y dot. These are in task space. And what is Q dot? Q dot is theta 1 dot and d2 dot. These are in joint space. Right? This is an RP manipulator. The first joint is a revolute joint. The second joint is a prismatic joint. So if we can expand this thing, what is mu dot? Mu dot is x dot, y dot. This is nothing but if you take the derivative of these equations, that would be yeah, d2 sine theta 1 dot plus, I'm basically using the chain rule because it has two variables. Then d2 dot cos theta 1 and y dot would be d2 cos theta 1 dot plus d2 dot sine theta 1. And again, writing this expression in this matrix form, this would be mu dot, this is x dot y dot, this would be minus d2 sine theta 1. Then what else do we have? Cos theta 1, d2 cos theta 1, sine theta 1. This would be theta 1 dot, d2 dot. Right? This is mu dot, and this is j of q, right? And this is q dot. I hope you can follow that. Yeah, I've got an answer as option 3. Is that the correct option? Yes, I guess you're right. That is indeed the correct option. So the constituents of the Jacobian matrix is nothing but if we have dou mu1 by dou q1, dou mu1 by dou q2, dou mu2 by dou q1, dou mu2 by dou q. Right? Like you can apply this generalized formula for constructing the Jacobian matrix for any robotic manipulators. Right? And here we have dou q1 by dou t, dou q2 by dou t. And on the left hand side, we have dou mu by dou t, mu1 by dou t, dou mu2 by dou t. That's about it. So the correct option is indeed option 3. That is indeed correct. So moving on to question 8. It says given below is schematics of an RR manipulator. Choose the correct condition for singularity when theta 1 is pi by 2. So be careful, like earlier we used a different convention, like we use theta 1 to be measured from the z-axis. Theta 2 we would basically refer it from theta 1 actually. Like for the convention that we use during our course, we would use theta 1 to be this angle. But in this problem, it is given again with respect to the fixed x-axis. Right? So the question asks the correct condition for singularity when theta 1 is pi by 2. So the correct answer is, as per Saurav, it is again pi by 2. Because that is indeed correct, because if this is x0 and this is y0, and Theta1 is given to be pi by 2. So this is the first link. This is theta1 pi by 2. And we again have this x-axis. Theta2 should also be fully extended like this. In order for the robot to be singular. And due to the fact that theta2 in this problem was given with respect to the fixed x-axis, the condition for singularity is again theta2 is pi by 2. Again, you can check this condition using the Jacobian matrix. If you assemble the Jacobian matrix and if you take the determinant, you can see if you substitute theta1 as pi by 2, if you solve the determinant, you can see that by making theta2 also as pi by 2, the determinant would vanish. That can be tried on your own. So yeah, the correct answer is indeed theta2 is pi by 2. Okay, so question 9, it says for a given manipulator, the Jacobian matrix J is given as such. If the end effector force is given as such, then what will be the joint space input vector? So like, for example, like if you have a manipulator and for example, if you have a three-dimensional manipulator, if we are given fx, fy, fz, the task space variables as 203, the forces in the task space variables as 203, and we have since the robot has 3 degrees of freedom, it will have 3 joints. You have to find out tau1, tau2, tau3. The torques or the forces that you apply at the joints of the robot, right? So that it can maintain static equilibrium. So how do you do that? Yeah, I got a question regarding the previous question. If theta2 is with respect to theta1, then theta2 is 0. Yes, I agree with that. Sorry if I'm again backtracking to the previous question. Just to clear this out, if this is theta1 with respect to the global x-axis, and theta2 is given with respect to theta1, so irrespective of theta1, theta2 should always be 0 for the robot to be in singular configuration. So it does not matter if the theta1 is pi by 2, it does not matter if it is 3 pi by 2, does not matter. Theta2 should always be in line with theta1. They should lie in a straight line. So if that is the case, then theta2 will always be 0 for the robot to be in singular configuration. Yeah, so coming on to the problem 9, we were asked to find out the input torque vector. So you might recall how we derived the mapping between F and tau. Like we basically derived it from the principle of conservation of power is F dot mu dot. We basically derived this from this conservation of power equation. And we ended up with this expression, tau is J transpose F. And we have been given J, we have also been given F. Then it is only a matter of matrix multiplication. Right? So J transpose would be 1, 2, 0, 0, minus 1, 2, 0, 2, minus 2. And F, as per the problem, is 203. So if you multiply this out, what will you get? It will be, what is it going to be? It is going to be, I suppose it is 2, then 4, 6, this is 10. Then the third row would be minus 6. 2, 10, minus 6. I hope that is the correct answer. Option option, the final option, I guess, option 6. Yes, option 6. Saurav also has said to be option 6. Yes. So the correct answer is indeed option 6. Yeah. So we'll move on to the final problem of this weekend. It says the workspace interior singularities in an RR manipulator occurs when the manipulator is fully folded back on itself. Is it true or false? So for an RR manipulator, it can have singularities at when it is fully extended, like so, like this is the first joint, this is the first joint, second link. This is the end effector. This is fully extended. And the fully folded configuration would mean like the first link goes from the base to the distance where its link length permitted. And the second link would come exactly back to the first link, just like this. These two lines are basically collinear, but I'm just showing it just for the sake of clarity. This is fully folded. So the question says the workspace interior singularities in an RR manipulator occurs when the manipulator is fully folded back on itself. Is it true or false? We don't have any answer for this. Should I go back to the definition of interior singularities? So like interior singularities basically says the singularities that happens within the workspace of the robot, not at the extremities of the robot. But as you can see, the fully folded singularity and the fully extended singularities both happen at the extreme ends of the robot, at the extreme ends of the workspace of the robot. See, like if this is the fully extended position, the workspace at the fully extended configuration will be of this shape. It will be of a circle, right? With radius, if this is L1 and this is L2, the boundary of the fully extended workspace would be L1 plus L2, right? And the fully folded workspace, the extremity of the fully folded configuration would be another circle that is L1 minus L2, depending on which of them is greater. So basically, these are both workspace boundaries. And the fully extended singularity occurs at this extreme boundary, and the fully folded singularity occurs at this extreme boundary, right? So both of these occurs at the boundaries. It does not occur within the workspace. So within the workspace is the area that is within these two circles, right? Within these two big circles. So like for an RR manipulator, there are no singularities that occur between the two extremities. So in that regard, the answer is indeed false. It only occurs in the boundary. It can a robot can have different multiple boundaries also. It does boundary does not mean the extreme. The boundary does not limit itself to this particular case. This can also be a boundary, right? And if L1 and L2 are equal, this smaller circle will vanish. It will vanish to this point. If L1 and L2 are identical of same length, if it goes upward by L1, it can come down by L1 itself. So there won't be an inner circle, an inner workspace boundary. Yeah, so in that regard, the answer is indeed false because there are no interior singularities for a RR manipulator. Right? Yeah, the explanation is workspace interior singularities generally occur when two or more axes line up Such a scenario never happens in an RR manipulator. That's indeed correct. And the two cases of singularities that we have encountered are both workspace boundary singularities, not interior singularities. Okay, so yes, that is about it. That's about the content of this weekend. I will have to address the concern put forward by Perumal Sami that says for assignment 3, Q15 option 4 is also correct. Okay, so I'll see what can be done for this case, right? I'll raise this with NPTEL team and we'll proceed it accordingly. So thank you for bringing this into my attention, right? Okay, so again, that's about it for this week. Next week, we'll discuss some problems and some concepts regarding dynamics. So you might have already started an introduction to dynamics in week 4 itself. Week 5 is mostly related to dynamics, mostly is dedicated to dynamics and simulation of robot dynamics in MATLAB also. So yeah, so happy learning. I wish you all the best for the upcoming assignments. So yeah, thank you for joining. Unless you have any doubts or queries, let me know. Otherwise, you can all log off. No more queries. Okay. Okay, then thank you.